Glory, welcome to part 3 of probability. From the previous video, that is part 2, we looked at the sample space and we introduced a number of definitions, sample space, the events, and so forth. So with that knowledge of what a sample space is, what an event is, today we shall proceed to look at part 3 of probability, where we want to look at exhaustive events, the general rules of probability, the addition rule, and then we shall conclude by looking at the marginal probability. Now to begin with, we want to understand what do we mean when we talk of exhaustive events. Now, if we have got any events, remember from our previous discussion, we said an event is simply a subset of the sample space. So suppose that we have A1, A2, and so on up to AN. Suppose these are events. So we define these events to be exhaustive if the sum of their probabilities, that is the sum probability of A1 plus probability of A2, if you add all their probabilities up until the probability of AN is actually equal to 1. So if you add probabilities of events and you get 1, we call those events exhaustive events. Now, a simple example is when you flip a coin twice. You flip a coin once. So the probability of having it landing head is actually half from our previous discussion. And the probability of getting a tail appearing is equal to half. So if you add the two probabilities for these events, you will get 1. In other words, probability of head plus probability of tail will be equal to a half plus a half. That will give us 1. So we can simply say event getting a head and a tail is said to be exhaustive. And I want you to appreciate the fact that getting a probability of 1 means the events in question are a sure event. If an event has got a probability of 1, it simply means that no matter what, that event will happen. So when you flip a coin, when we are saying you get a head or a tail, there is no way each of these two will not happen. So that is why we say the two are exhaustive, because they make up the entire sample space. So now let us move on to look at the general rules. You see, when we talk of general rules, these apply to probability theory in all aspects. So now, suppose that we have got an event A. So I'm looking at the general rules here. Suppose A is an event. I want you to remember the complement of event A. The complement of event A, we write it as A complement, or simply A with a small c on top. That is, event A will not happen. So, general rule number 1, we are saying the probability of an event A is a non-negative number that lies between 0 and 1. This is a general rule number 1. Probability of an event is between 0 and 1. And in fact, these rules are also called axioms. Axioms, it means they are self-evident. These are the building blocks. We know them to be like that. So the probability of an event is between 0 and 1. Number 2, what we also know is that the probability over the entire sample space is a sure event is equal to 1. So that is a sure event. Also, what we know is that the probability of an empty set, the probability of phi is equal to 0. And I'm sure we all know what an empty set is. So Now, suppose we've got A and its complement. What we know is that the probability of A plus the probability of A complement is equal to 1. This is very, very important. If we take A to be the event that it rains on a particular day, it means A complement is the probability that on that particular day it does not rain. So, if you say probability of A plus probability of A complement, it then means that if you add up the two, you must get 1. Why? Let me give a simple example when we weather forecast. When they say there is a 10% chance that it will rain. 10% chance it will rain, it means there is a 0.1% that it will rain. In actual fact, there is also a 0.9% that it will not rain. So if you add the two, you will surely get 1, because that is given in terms of probability, and raining and not raining actually refers to an event and its complement. So these rules are very, very important. This rule is what we call the complementary law of probability, and we need to appreciate it as we are going to use it, especially when we compute probabilities involving a Poisson random variable or a binomial random variable, because sometimes you are required to get probability of A where conditions are difficult for you to get it directly without applying the complementary law. I think we will see as we proceed to make with the topic on probability. Now, that is that with the general rules of probability. So a probability is non-negative. The probability of a sample space is 1. The probability of phi is 0. The probability of A complement is equal to 1 minus probability of A. Now, I want us to look at the addition rule. Addition rule. The addition rule of probability applies to two types of events. So there is addition rule as it applies to what we call mutually exclusive. Mutually exclusive. And there is also the addition rule applying to non-mutually exclusive. Now, from our previous video, we indicated that mutually exclusive events are events which cannot occur at the same time, whereas non-mutually exclusive events are events which can actually occur at the same time. And if we are to produce a Venn diagram to illustrate the two types of events, we will have something of this nature. So for mutually exclusive, they are also called disjoints. Let us assume that these are events A and B. A and B are totally disjoint. They are mutually exclusive. They cannot occur at the same time. They don't have anything in common. They don't have an intersection. So for non-mutually exclusive events, we have something of this nature. So it means these events A and B can occur at the same time. That is why their intersection is not an empty state. They have something, they intersect. Now, so what do we mean by addition rule as it applies to these two types of events, that is mutually exclusive and non-mutually exclusive? Now, I think I need to clean here. Now, the addition rule goes as follows. The probability of A union B for mutually exclusive is actually given by the sum of the individual probabilities. It is actually, probability of A union B will be just the probability of A plus the probability of B. But the probability of A union B for non-mutually exclusive, that is probability of A union B, will be equal to probability of A plus the probability of B, but we have to subtract the probability of A intersection B because the intersection is not 0. So what it means, remember A union B is actually the entire shaded region. We shade the whole of A and we shade the whole of B. But when the two are not disjoint, in other words, if the two are non-mutually exclusive, it then means that when you say probability of A, you are including also the intersection. Now, when you say plus the probability of B, you double count the intersection. So the idea of subtracting A intersection B is to remove the intersection once, so that what we remain with is actually the union between A and B. Now, this is an important rule, as you are going to see as we proceed with our topic on probability. Now, but what we want to do now in conclusion to this work, we want to look at what we refer to as marginal probability with wide application, as you are going to see from in this discussion. What are marginal probability? I want us to assume that we have got two variables, A, which is got M categories. So in other words, we've got variable A, which is category A1, A2, A3, and so on up to AM. And suppose that we also have another variable, we call it B, with categories A1, B1, so B1, B2, and so on up to Bn. Now, of course, I'm trying to give the general overview of marginal probability, but as a good example, you can have a classification table where we have, for instance, yield across different regions. So A can be yield levels, and B can actually be regions. So that is a classification. We can also have, for example, number of, say, B refers to regions, and the number of people across those regions with a certain level of education. So that is the marginal probability table. So what we are going to have here we will have number of B1 intersection A1 in terms of probability. This, what we have here, is the number of B1 intersection B2. So we proceed in that manner. Here we will have number of elements in B1 intersection A3, and this is number of elements in B1 intersection AM, and so on. So we might talk of our total here. So this here will be the number of elements in B1, the total number of elements in B1. If we proceed in the same manner, this will be number of elements in B2 intersection A1, and so on, number of elements in B2 intersection AM, and also this will be number of elements in B2. In the same manner, when we add downwards, this will be number of elements in Bn intersection A1. We can also get a total, so that what we have now at the end of the day, this is the number of elements in A1, this is the number of elements in AM, and this is the number of elements in Bn. I'm sure you appreciate how we are constructing the table. At the end of the day, this is the number of elements in the sample space, the total number of elements in the sample space. What is important in this marginal probability table, that is, we are just using the term marginal probability table, but actually this is a contingence table. It is just a contingence table, where we are cross-tabulating, or a cross-tabulation table, where we are cross-tabulating two variables. So one important issue here is to note that N of B1, the number of elements in B1, is actually given by B1, number of elements in B1 intersection A1, plus and so on up to plus the number of elements of B1 intersection AM. This is very, very important, because we want to use this fact as the basis for calculating probabilities. Now, I think to make you appreciate what is happening here, I'm going to use a numerical example to demonstrate the idea of marginal probabilities using a numerical example where we are going to illustrate the calculation of different probabilities. Now, look at this example. We have 339 farmers who are classified based on their ages and the farm sizes that they own. So the ages are A1 up to A4, where A1 is 20 to 29, 30 to 39, 40 to 45, and 50 plus. Then we also have the land sizes. There are those farmers with the small farms, we call that B1, medium, we call that B2, and the large farms, we call that B3. And I want you to take note that A1 intersection B1 is actually equal to the number of elements in A1 intersection B2 is actually equal to 31. That is very, very important. From there, you can see this is the intersection of A1 and B1, intersection of A1 and B2, and so on. Now, what is the number of elements in the entire sample space? Number of elements in S is equal to the total number of farmers that we have, which is 339. So, suppose the experiment involves selecting a farmer. Selecting a farmer randomly. This is very, very important. We need to indicate that it's a random process. Selecting a farmer randomly. So you may be required to determine the probability of selecting a farmer who is aged between 40 and 45. So what is the probability of A3? The probability of A3 is choosing a farmer aged between 40 and 45. So that probability is the same as the total number of farmers who are aged between 40 and 45 over the entire sample space. So that will be equal to 79 over 339. Now, what is the probability of B2? Probability of B2, and what does it mean in actual fact? Probability of B2 is selecting a farmer who owns a medium-sized farm. So that is equal to 60 over 339. And I think we can reduce this one to 0.1770. You see when that one is equal to 0.2330. Now, what is probability of A3? Probability of A3 intersection B2. And what does it mean? Probability of A3 intersection B2 means A3 is a farmer who is aged 40 to 45. B3 is a farmer who owns a large farm. So we want to select probability of A3 intersection B3 is the probability of selecting a farmer who is aged between 40 and 45 and owns a large farm. So we need to use this, the intersection, over the entire sample space. So the probability of A3 intersection B3 now becomes 29 over 339. Now, what is the probability, the final one, of A3 union B2? What is the probability of A3 union B2? And what do we mean here? Probability of A3 union B2. Are these events mutually exclusive or not mutually exclusive? What is A3? A3 is selecting a farmer who is aged between 40 and 45. And what is B2? B2 means selecting a farmer who is medium, who owns a medium-sized farm. So, I want you to see that the two events, A3 and B2, have got something in common. There is an intersection between the two. So, using the addition rule that we have illustrated for non-mutually exclusive events, we will have, this is probability of A3 plus probability of B2 minus the probability of A3 intersection B2. This is very, very important. So we will have, what is the probability of A3? We will have 79, the total number of farmers with A3, which is 79, over 339, plus the probability of B2, that will be 60, over 339, minus the intersection. The intersection is simply where the two intersect, B2 and A3, that will be 21 over 339. I want you to take note that when we calculated the probability of A3, we said 79. The total 79 includes also 21. So when we used 60 in calculating the probability for B2, the total for 60 also includes 21. So we have actually double counted 21. And so in calculating marginal probabilities, then we are going to subtract that 21 over 339 once because we've included it twice. Now, finally, so here you can actually work out, I think you must get 0.3481. When you simplify that one, you can use your calculator and so forth. Now, what is the probability of A4 complement? In fact, what is A4 complement? A4 complement in this scenario means selecting a farmer who is below 50 years. You see, A4 means farmers with 50 years and above. So any other farmer who is selected, who is below 50 years, we refer to that as A complement. So how do we get A complement? There are two ways to do it. So we can use the complementary law, and remember we said the complementary law, we said probability of A4 plus probability of A4 complement must be equal to 1. You see where we are now using the complementary law. What is the probability of A4? We look at the total for A4, which is 24 over 339 plus, but we want the probability of A4 complement. So this is equal to 1. So which means probability of A4 complement is actually equal to 1 minus 1 minus 24 over 339. So this will reduce to what? You can use your calculator. That should reduce to 0.9292. But alternatively, instead of using the complementary law, you can still get the same probability by just adding the total of all the farmers who are below 50, that is 79 plus 189 plus 74, and you divide that by the total number, by the total sample space. So ladies and gentlemen, we have covered part 3 of probability, that is the exhaustive events, the addition rule for mutually exclusive and non-mutually exclusive, the general rules or the axioms of probability, as well as the marginal probability. We shall proceed to look at dependency and independence of events, conditional probability, and finally the Bayes theorem. Thank you very much.